отвечать вы будете или кто-то?
Ну, не знаю, здесь как бы только одну кнопку нажимать.
Давайте я.
Просто нужен человек. Вот самый главный микрофон, чтобы кто-то приносил с третьего этажа. И тут как бы просто по окончании всего на стоп нажимать и все.
А микрофон надо как-то спарить с системой, если его принести?
Нет, он сюда автоматически подключен. Ага. Не, как бы вот 427, 108 там все лежит. Да.
А если типа у нас семинар, и все говорят, можно сюда даже?
Ну, если честно, я не знаю. Ну, вот Хорошкин, кажется, записывался, и там просто передавали звук в руки микрофон.
Ну можно так.
Можно так, да. Ага.
Хорошо.
Ну, держите.
Ну ладно, уже типа идет, да?
Ну да, идет. Да,
А стоп это вот это?
Стоп это... Нет, вот трансляция, вот здесь вот на это черное. Да, нажать и все.
Окей. То есть мы уже на YouTube.
Ну да. Ну все тогда.
Да, хорошо, спасибо. Это вот так. Да? Здрасте. Ну, пока что сегодня лекция. Это по... Окей. Кто-то знает, я вообще правильно эту штуку одел? Так примерно должно быть? Не, ну это знак перед лицом, то это вообще... Ау. Ау. Ну, я свое дыхание слышу так. Вот тут колонка.
Громче должно быть слышно из-за того, что вы говорите, да, потому что он включил колонку.
Окей, значит, я по умолчанию должен сейчас язык сменить на английский. Alright, so by default, I have to speak English. I don't know. So I guess you do not speak Russian, right? Alright, so this is already enough to do it in English. I think at least one more person who doesn't speak Russian is watching YouTube, I guess. So, all right. Well, welcome to Lee Groups and Lee Algebras 2. My name is Philip Uvarov. I will be a lecturer and seminar leader for this course. All right, so let me first talk about some organizational stuff. Maybe I should use first this one. Okay, so first things first, grading scheme. So your final grade will be calculated by the following complicated formula. Well, you can go over 10, but then we will get 10 officially, so minimum out of 10 and 0.6 S and 0.6 E, or I don't know, whatever T. So S stands for seminars, so it's out of 10. And T stands for tests. There will be 2 of them. So, okay, so your final grade consists of 2 parts, seminars and tests. Okay, now about tests first. We will have something in the middle of semester and something at the end of the semester. So T is T1 plus T2. And they are of the same value, right? In the middle is about the first part of the material. At the end, about the second part of the material. Moreover, you can take the first test, and at the end, you can decide that I don't like the grade for this test. And then you'll just let me know and take T1 and T2 at the end, right? So for T1, you kind of have 2 attempts, if you wish, all right? So if you don't like what you did in the middle semester, sometimes it's busy time, so you just didn't learn enough or something. You'll just have like twice more problems at the end, and that's it. But you should choose in advance, right? Do you take the first part again or not?
Do we have the same time for the same set of problems, or like we have to like?
Yes, it is the same. Yes, just problems. Maybe some with some variations, but not crucial variations. Maybe some numbers or different groups, different algebras, but pretty similar.
Yeah, no, my question was more about, you said that we get T1 and T2, right, at the end. So do we get it at the same time, or it's a separate test?
You get it at the same time. So each will be like an hour and a half, right? So final is 3 hours, right? And so if you're taking just T2, you have an hour and a half. If both of them, 3 hours. Yeah, I mean, this is something I came up to. There might be some flaws in this plan, so I mean, this is all negotiable. Okay. Right. As for seminars, any questions about this? And they might be online, maybe offline. I'll decide. Maybe partially online, partially offline. So I don't know. Anyways, so for T, the maximum is 10. So for S, right, I really would like you to work on seminars, not me just explaining problems. And usually, like the second thing happens because, well, I already thought about problems, right? So I have some advantage. So the seminars will be like that. So we are going to try to have seminars first and then lectures. And for seminars, I will send you so today is Thursday, so on Friday or at latest on Saturday, on a bad week, right? I will send you the problems for the next seminar, all right? And then you have almost a week to think about them. Then we have this Google class that I created, and the link is in the Telegram chat. So you can solve some problems and upload it, your solutions to this Google Classroom, right? And then on a seminar on Thursday, and you can do it all the way up until the seminar, right? Which is 14:50 on Thursday. And so on the seminar, I will just give you, before the seminar, I'll give you a list with your names, and you can put which problem you would like to present, okay? And so your S is your grade for presentations or possible presentations. Of course, there's a lot of you, right? So if a person solved a problem, but there are, if there are many people solved the problem, then I mean, not everybody can present their solutions, right? So I'll just look at who wanted to present, right? And then after the seminar, I will go to Google Class and look at your solutions, right? And then it will be, you know, either check or not check for this particular problem. And then you will get, so if for each seminar you solved like 2 problems out of list will be, I don't know, maybe 5, 6 problems, depends. All right? So I don't know. It's just the goal really is to encourage you to talk on seminars and attend seminars, and not. I will work on lectures, you on seminars. Yes, 10 is 2 problems, so presented problems. So S equals 10 on for each seminar. And it is, I mean, it is accumulative. So you might not solve any problems for one seminar, but solve 4 for another one, and this will be, I mean, the same grade. All right. Moreover, I think that it is fair, only fair, if S might be greater than 10. So if you are solving like 4 problems each and ready to present it like each week, then I mean you can get your 10 and not even do tests. I mean, yeah. Yeah, like I don't know, 3 problems, but you should be here and should be ready to present any problem that you, right? So I think it's a fair deal. Any questions? All right, so this is about grade. Now, what is the course will be about? So, what we will discuss. All right. Well, it's kind of hard for me to plan for the whole semester. It's a big semester, right? We'll have all the time until June, right? So we'll see how it goes. So the plan is the following. First, we will talk about structured theory of Lie algebras. Mostly semi-simple Lie algebras. And so the goal is in some in one way or another to see classification of simple Lie algebras, right? Maybe lacking proofs of some, you know, very well statements with the brutal proofs, but the goal is here is classification of simple Lie algebras. Also, representation theory of simple Lie algebras. And by Lie algebra on this in this. Okay, so these two items are for finite dimensional Lie algebras. All right. So finite dimensional, and here's finite dimensional. So here I will discuss some things like roots. I mean, here and here, they both matter. Roots, weights, highest weights. So we saw this for SLN, GLN, but now it will be a systematic study. So all this is present for all simple Lie algebras. So these two things will mostly follow the book by Alexander Kirillov, Jr. So following the book by Kirillov. Yeah, so it's called something like Introduction to Lie Groups and Lie Algebras. And it is actually starting with chapter 5 and until actually the end of the book. So starting chapter 5. So that's the main textbook for this. It's missing some proofs, so maybe we'll also skip it. Maybe we'll go to some other stuff. So we'll see. And after these 2 points, we will see at which point of semester we are. So originally this course was planned to be taught by Evgeny Feigin, right? And this is the plan that is in the textbook. But we'll see. The semester is big, so I think we can do more than that. And there are possible ways where we can go. So these two parts, they are not about Lie groups at all. So of course you can translate it to Lie groups, some of the results. But mostly we'll talk about Lie algebras. What concerns a lot Lie groups is, I don't know, you might call it some maybe Fourier analysis. On compact Lie groups. All right. Well, so actually, well, if somebody remembers, what are irreducible finite dimensional representations of S1? Can you tell me? So S1, I think about S1, right, as elements inside C, right, of such form. So this is a chart, right, that covers almost everything. For another point, I need another chart, for example. Right, and all irreducible finite dimensional representations that they actually one-dimensional complex, I mean. They are one-dimensional, and they just take this to this. where k is actually some integer. So all finite dimensional representations are irreducible representations of S1. So why I'm saying this? Because to link it with Fourier analysis, right? So therefore, any function on S1, which is L2 function, in this chart is just L2 function of phi, right? I can approximate by this, right? But these are also given by all finite dimensional representations of S1. And this has some generalization for any compact group. These are also some solutions of Laplace, some differential operator, and this also has some generalization to compact Lie groups. So this is one thing, we didn't cover this. I don't know. So I guess some people here which study Lie groups and Lie algebras won this fall, right? And the others the year before, right? Do we have somebody who actually studied it even before that? Oh, you. Okay, so you studied with Leonya Rybnikov, right? And he talked a little bit about the stuff, about Haar measure, right? And orthogonality of matrix elements of representations. So this is it. So I didn't cover it because, we took it by different pace. So anyways, this is one way to go. And another one is actually go to infinity. So maybe infinite dimensional Lie algebras. So this 3 and 4 we'll see. Maybe we'll not cover them at all. Maybe we'll start with this one. So I don't know. And I am open to suggestions. And but of course I will decide on, how comfortable I will be to speak about any of this. I'm more comfortable to maybe to speak about this one than this one. But we'll see. So this includes. To study all infinite dimensional Lie algebras is, it's a very complicated problem, and there's no, any organized theory about that. But there are Katz-Moody Lie algebras, and inside Katz-Moody Lie algebras there are affine Lie algebras, and actually they possess a lot of theory. Related to the first two items, but even more, some generalizations. So, so standard literature about this is Helgason and also Zhelobenko. I don't know. So if I will talk about this, then I think I will follow Zhelobenko compact Lie algebra. Compact Lie group. And the standard literature here is Katz himself. Something like infinite dimensional Lie algebras, it's called like that. So that's the plan. And this semester we even have like a, I even named like your book that I am going to follow, so you can just, if you miss something, you can go to this book and read. So anyways, that's the plan. Any questions? Suggestions? Yeah. So again, seminar. First we'll have seminar and then lecture starting next week. So today we'll have just a lecture, and maybe we'll not have 2 hours. So we'll see. Where the second hour we'll spend on something that I planned but had no time to include in the first hour. So. All right. Right, so let me start here. I'm still need to understand the logistics of this, of a lot of space that we have here. All right. So today we'll talk about nilpotence and solvability of Lie algebras. All right. So nilpotent and solvable Lie algebras. Yeah, chapter 5 of Kirillov starts actually with Poincaré-Bergov-Witt theorem. But I assume that we already know what it is. So we start with something new. So first, let us, we need to start somewhere. Let us recall what is a Lie algebra. So Lie algebra G is a vector space. Of course, you all know what it is. With a linear map from G tensor G to G, or bilinear from G cross G to G, whatever. Well, actually, it's denoted like that, right? So it's bracket such that, so we'll say it's Lie bracket or commutator. First, it's antisymmetric. And second, so I have minus here. And second, I have the Jacobi identity, right? So I need to draw it like this. And put x, y, z here, and then cyclically permute it. So z goes here, x, y, and then y goes here, zx. Right. Well, I guess these are not the news for everybody. In particular, such a structure we have on a tangent space to identity for a Lie group. So the next notion that we would like to discuss is what is an ideal. So if I have I inside G, it's an ideal. If what happens? Well, it is a subalgebra, right? So subalgebra. And if I consider the bracket of x, y, so bracket x, y lives in I for any x in G and y in I. So not only it's subalgebra, but also if I consider bracket with something outside of it, then it's also inside I. Yeah, I'm sorry, so it's like this. Yeah. And of course, it's trivial. Well, and here you see. So we also have ideals in rings, right? But there we can have right and left ideals. So here there's no difference, right? Because the bracket is antisymmetric. Also, if I have I1 and I2, they are ideals, then of course it's an easy check that, well, intersection is an ideal, sum is also ideal. And the third example of how we can create another one is what we'll denote like this, like a commutant. So R ideals. So who is this guy? So let us. Okay. So this guy, just to see that we're on the same page, is just all elements that are given by xy, where x is in I1 and y is in I2, right? It is inside intersection, actually, right? Well, if they are ideals, but sometimes we can consider this are not ideals, but some subalgebras, right? Well, in this context, we would like them to be ideals, of course. All right. What next? Okay, so next, let me define what is called derived series. So definition of derived series. So derived series is actually a bunch of ideals inside the Lie algebra G, and it's defined recursively. So I have D. Let me define dG to be the commutant. And then let me define D with upper index I of G to be the commutant of di plus 1G, I minus 1G, di minus 1G. Right. And so the collection of this DISG is called derived series.
How to say derived series in Russian?
Производный ряд. All right. Now another definition. G is called solvable Lie algebra. If and only if, well, D and G equals 0 for some n, well, for some n. Now let us prove a first statement of this course. Yes? In the first definition. No, that's just, well, you could have it like that.
So could you say like?
Yeah, right. Yes, you're right. There's a definition is not complete, right? Otherwise, right? D, yes, D is D0, right? Or D0 is. Do I want? No, I think actually not even 0, but 1. Yes.
I guess you want to have current extent, no?
Yes.
Yeah, so the 0 is just G.
D0 is just G. Say it again. Here, span of this is the same as this. If I have z x1 y1 plus x2 y2.
Yeah, actually, what is it?
Can we?
I think you have to span it.
Yeah, I would like to maybe no. Yes. So if it's not the same as x1 plus x2, right? y1 plus y2, because I also have these terms, right? Yeah. Yes. Mm-hmm.
We have x1, y2 and plus x1, y2 and minus x1, y2. Yeah, that's a good question. What we can't do that the last one and just minus the brackets that we don't want.
No, but we still need span, right? What I said here is just elements like that, right? So I would like to present it just as one bracket. So. Yeah. Okay. Good. Now, so this is the definition, and so I don't know, theorem, proposition. The following are equivalent. First, G is solvable. And the second, so there exists a sequence of subalgebras let me go maybe let me go here. Sequence goes like this. So by A0, I denote G itself. And then inside have A1, then A2, and so on. And then some K, which is actually 0.
Closed under the bracket map. So like bracket of A1 should be less than A1.
Yeah, I didn't finish. Yes, so there's not only this, but also such that AI plus 1 is an ideal in AI. I guess that's, and also AI quotient by AI plus 1 is abelian. Yeah, by the way, we have all this the standard theorem, right? Why first of all, why do we need ideals? Because quotient by the ideal gives me subalgebra. Well, in this case, it's Lie subalgebra, right? Okay, so proof from from 1 to 2. What should I do? I just can take I to be DIG. Then what happens here is, well, of course, so well, we can check, right? So then I quotient by AI plus 1 is AI quotient by AI plus AI, which is of course abelian. Yes. And the other way around, from here to here, I would like to see, so it means if I have such a sequence, then D actually it becomes 0 at some point. I would like to prove, so claim that AI actually includes D I G. Let's prove it by induction. So proof by induction on I. If I equals 0, then I have G, and of course it contains D. Well, it contains itself, right? If I equals well, and then step of induction. So step. All right. So I have so let me take di, right? This is by definition di minus 1g, di minus 1g. And that's it, right? This is by induction assumption. This is in I minus 1, and this is in I minus 1, right? All right, but since this is abelian, right, this is inside AI. So this is because of this condition. AI over AI plus 1 is abelian. So commutant is actually the smallest or minimal with respect to inclusion subalgebra, such that quotient, ideal, such that quotient by this ideal is an abelian algebra. So that's why it happens. I mean, there's should be some easy check, but we are easy. So we proved, right? So at some point AI becomes 0, therefore at the same point, so and there is K. Okay. And let me now go to the first word. So the next is, so these are solvable. So now let us define nilpotent. For nilpotent, we also need some kind of series, but this time it is called lower central series. Okay, we can speculate why after I give a definition, but I don't know. For sure, I don't know. So, again, we define D. So now index will be at the bottom. So define D1 of G is the same as D, G, right? And the same as D1 with upper index G. Should I write like this? But then Di G is defined as follows. It's a commutant of G and Di minus 1 G. And here comes the definition of nilpotently algebra. So nilpotent, so G is nilpotent if and only if dn G is 0 for some m. And of course, here we would like some equivalent definition of such kind. Right, so let us formulate another proposition. So proposition, I don't know, I don't, usually I don't enumerate propositions, maybe it's my mistake, but we'll see how confused we will be at the end of the course. But anyways, so proposition is of the same sort. The following are equivalent. G is nilpotent. And second, again, there is a sequence of, let's just say right away that they are ideals. In the previous case, this, yeah, I mean, too much. There's a sequence of ideals. I guess I should continue here. Yes, they are. Yes, they should. Let's. Should be. Yes. We can check, but.
We didn't really prove that the commutative of two ideals is actually an ideal, but it follows from G-commutative. Yeah, it
yes.
actually follows from equivalent, and that's why we need this map.
Okay. Yes. All right. So let me finish. So there's a sequence of ideals. Again, I need A0, which is G itself, and then one is inside another, and the last one is 0. And I would like the following: G with I. Well, since AI is an ideal, it's inside AI, right? But I would like more to this to be inside AI plus 1. So such that proof. So proof is similar. I don't know. So if from 1 to 2, let me again put AI to be D now lower index G. And then this happens. Well, let's check this one, for example. So I need G, well, just by definition, I don't know. Nothing to check. Right. From 2 to 1, again by induction, the same thing. AI, inside AI I have Dij. And again by induction, on I. So maybe let me not do this. It's the easier one step thing. Okay, So now we have nilpotent and solvable. Now we need some examples to think about, right? Actually, I guess when this mathematics was created, people thought the other way around, right? They had the examples and then, but okay, so the lecture is going like this. Examples. So we will have actually just one example, but this is very important example because it's kind of structural. So example is about upper triangular matrices and strictly upper triangular. And I will formulate it like this. So suppose that I have a flag, F. What is a flag? It's a collection of subspaces of some vector space. Yeah. By the way, again, so our just to like a disclaimer, right? Our field is always ROC, right? And for representations, I think it will always be C. Like for now, it might be ROC. But again, you might sometimes like additional thin moments that you have to think about. I mean, for R and C. Well, maybe you can raise some questions and we'll discuss it. Anyways, so flag over R or C, and then we have this, and the last one is V, and I would like it to be a full flag. It means that dimension of Vi is what? I. Yeah. Well, dimension of V is so F is full. Or complete. I don't know. I think it's the correct term is full. Anyways, so then I would like to define this algebra. It lives inside GLV. And these are, well, transformations, right? Well, X inside GLV such that X, if I act on Vi, right, it's actually inside Vi itself. So it never goes outside of Vi. And then N of F is X in GLV such that XVI is V, and what should I write here? I minus 1, right? Yes. So these are upper, these are strictly upper triangle. Yep.
Strictly upper, there's zeros over there.
Yes. Yes. And okay, next board. I think I should enumerate them before the lecture, just not to be confused. Anyways. I never touched this one before. So. Right, so after this one, I'm going to do this. Remind me if I'll do otherwise. Was that? Ah, complete. Okay. Yes. Okay.
Yeah. I watched Wikipedia. They say complete.
Yeah. Well, usually language-wise is.
No, just this terminology. It's not just.
Yeah.
It's a dictionary.
Let's add. Where was it? Ah. Ah, yes, here. Full, complete. All right. So then the proposition is the following. N of f is what? Nilpotent, and B of f is solvable. And in simple algebra in the future, we'll have triangular decomposition, and we'll have in this triangular decomposition nilpotent, and like what's called Cartan subalgebra, and direct sum of Cartan and nilpotent is solvable. Yes. Okay. So anyway, so all this is makes sense to explain just for the future. So that's my point. Let's prove this. So proof. Proof is also very easy. You just need to find the right ideals AI. Let us define them as follows. These are X in GL V such that X acting on VI, well, I is not good, L is VI minus L. Then what? Then A0 is B, and A1 is actually N.
X on VI is E. It's not include VI.
Sorry, yes. Includes. Yes, it's a flag or the filtration here. All right. And I would, so the first very easy observation is that A, K, AL, commutant of this, is inside A K plus L. Right? No, because what is this? These are we have elements of the sort x y minus y x. I mean, sums of this as we figured, right? But let's just consider one of them. And but in any case, if y is from here and x is from here, then the composition shift by k plus L this index. right? First I shift by k, then by L. And the other way is this the same. But so, of course, if this, if x lives in AK and y lives in AL, then this lives in AK plus L. This means right away that n is nilpotent. So why? Oh, first of all, we have this inclusion. This all actually they are ideals, right? For example, because of this rule, and it's a sequence of ideals, right? So I have n, which is A1, and then I have A2, and so on. And the last one is AN. It means that I shift Vn to V0. V0 is 0. So AN is already 0, right? Then, so to check that this one is nilpotent, we need such sequence of subalgebras, and also we need that I quotient by I plus 1 is abelian. Oh, it's about solvable. No. Okay, then we need so we're checking n is nilpotent. Then we need A1, right, which is n, commutant with AI is inside AI plus 1, which is also true, right? This is n. And by our proposition, this is therefore n is nilpotent. But for solvability, we need what I tried to say before, right? But so actually, B is a little bit bigger. Okay, I'm not going here. I'm going here. Right. So B. Yes.
Why do we say that bracket is a commutator? I suppose we just say that some Lie algebra with some linear operator on its tensor product. With that we say it's a bracket. So why there we use the bracket of AKAL? It concludes element like the commutator of x and y. Just to understand why we use bracket. So commutator is sum. It's
Yes, sure.
Can be used as a bracket. But
Right. But this is a concrete example. Here, our bracket is something. It's a good question, but actually, we also know Ador's theorem, since we work with finite-dimensional Lie algebras. We also know that all finite-dimensional Lie algebras are subalgebras in GLV for some V. So for Lie algebras, this is kind of justified in any case. But here you don't even need to think about this. This is some concrete example, and you know what is the bracket, right? You know what is the bracket for GLV. All right. now B is A0, then inside we have A1, then A2, and so on. And we would like to prove that I quotient by AI plus 1 is abelian. And this is actually true and just follows from this one, from this one. For I greater than 1 or equal. So if I is not 0, then this follows, right? Because AI is inside A to I, right? Which is, if I is greater or equal than 1, then this is inside AI plus 1, right? So if I is greater or equal than 1, which means that AI over AI plus 1 commutant inside is abelian. But what about A0 then? So A0 is B itself, right? So I need to check that B is inside N. Then I'm done, right? As here is where we need the completeness or fullness of this flag. By the way, well, all the definitions work, and N of F will be important for any flag. But B of F is only for full, because you have these blocks inside, right? Which, if you try to, to see what are derived series, they will never go to 0, these blocks. They are like GLNs inside bigger GLN. Anyways, so why is that true? Well, we need to just look at some bases, right? So V1, Vn is the basis that is corresponds to this flag, right? So Vi is inside Vi minus Vi plus 1. All right? Or maybe the other way around. Yeah, I minus 1 is inside I. Okay. Then I have, let me just take x in B, x and y in B. Right, then, well, x acting on Vi is some Ci Vi plus something else, but with indices smaller than I, right? And y Vi is some number Di times Vi plus something else with which is the span which is inside here, right? Now, if I compute the commutator, apply it to Vi, right? It will be Ci Di minus Ci Di, Di Ci, whatever. This is the coefficient for Vi. And then plus something that lives in Vi minus 1. Therefore, commutator shifts it to at least one step down, right? So therefore, it lives in. So therefore, commutator is in N. So we proved. Yes. Okay. So we need to finish some in 5 minutes, right? Or maybe less than that. Right. Let me give a couple of more easy statements, and then we'll have a break, and then continue because, yeah, I spent a lot of time organizational stuff. Yes. So let me first use this one. First easy statement is that if being nilpotent is stronger statement than being solvable. So if G is nilpotent, then it's solvable. So proposition. Proof is also, we need to see that D with lower index G is inside D with upper index G. Okay, let me. If nilpotent, yes, should be the other way around. It means that the 0 and this. Yes. So let's check, right? By induction. Almost all the statements today we just proved by induction. So by induction, I don't know. Should we check on that? For D1 is clear, then D0 is clear, yes. But D1 they're also the same. So Di G is Di minus 1 G Di minus 1 G, and then this guy is inside G, this guy is inside Di minus 1 G with lower I minus 1. And so this is inside Di. That's it. Also, there are some obvious things, like if G is solvable nilpotent, then any quotient of G by an ideal is solvable and nilpotent. It's just follows almost directly from the definition. And one last easy statement, and then next statement will not be so easy, and for the next hour is the following. So if I, it's an ideal inside G, is solvable nilpotent. It's that I kind of forgot. Yeah, quotient, and then I want everything else. Okay, let us. I kind of forgot solvable nilpotent. Not so crucial the statement. So let us go to the break and start fresh in 10 minutes.
семинаре линейный оператор, мы использовали его как будто он коммутатор. Или это типа семинар? Почему так? Ну, то есть...
Ну, вообще нет. Здесь вроде нет.
Ну, фактор по
Нет, вот
линейный оператор. Или
здесь я пользовался тем, что вот это лежит внутри вот этого.
Да, это правда. А почему вот это?
Почему вот это лежит внутри...
Почему вот это?
Есть какими-то крутыми чуваками,
Нет, это даже не лежит, то есть это радость.
Это потому что по определению, что такое абелева алгебра Ли. Это та, в которой все скобки нулевые, без всяких коммутаторов.
То есть мы имеем... Да, а еще насчет того, что у нас это векторное пространство,
Да.
с там, ну вот с скобками, да. А подал, что мы имеем в виду, что там тоже векторное пространство с определенным ним скобочками.
Оно замкнуто относительно, да, это, да. Ага. Да,
Насчет пересдачи хотел узнать, там в табличке написано, что на связи с преподавателем. Это что значит? Что вы...
Не
То есть просто
знаю.
имеется формат пересдачи какой и что там будет вообще?
А вы Дмитрий, да?
Да.
Формат тот же самый,
То же
что...
самое, те же самые
Просто
задачи
я
решаете?
вам, да, просто пошлю по почте. Ну, там другие какие-то задачи,
Ну,
ну, такого
понятно.
же плана.
А.
Вот. Ну, они как бы прям
Такой
тематика
же-
такая
да,
же, все то же самое. Вот.
Не, просто чтобы знать, что ты готовишься. Там, если холодно, там нужно теорию подучить. Если... Я поэтому
Не.
То есть задача.
Это будет экзамен. И как бы это сложится с вашим накопом. То есть для первой пересдачи правило именно такое, что как бы складывается с накопом. Вот, если там комиссия, то это как бы все обнуляется.
Да.
Сейчас, сейчас же нам, наверное, стоит перейти в 213.
А у нас вроде просто...
Да, извиняюсь, мы здесь остаемся.
Да?
Вроде да.
А тут, я так понимаю,
кто-то
кого-то
еще?
еще есть. Артем, у тебя что-то есть? Вот.
А мне, значит, Гоша
Да?
сказал, что он все уладил. Посмотрите расписание, да. Мне
На
кажется,
сайте висит, что у нас здесь.
да, он мне сказал, что здесь.
А у вас тут пара?
Да, по-моему, все поменялось, да. Там все меняется с каждой минутой.
А что у вас за пара? Да,
Нет,
какой-
логика, алгоритм или что такое?
логика алгоритмов
Не
это...
логика,
Сейчас это четверг, да?
четверг, да.
Это, видимо, в курсе по выбору.
Видимо, да.
Да, тоже стоит 427.
Да?
Это же ваш?
Тоже 427?
Да, тоже стоит 427.
О боже.
Что происходит?
Надо, видимо, учебную часть видеть.
Сейчас, ну нам...
Мы поменяли вот буквально сегодня. Я думаю, что то, что нас записало 45 человек, и на первый раз решили дать
Так, а мы выключились пока или чего? Я даже не знаю.
Что-то идет.
Давайте пока не будем выключать на всякий случай.
Так, а мы уходим или не уходим?
По плану, как сказал человек, который суетился здесь, мы не уходим, но, видимо, это как-то не соответствует другой реальности.
Я получился сейчас раз, не заканчивал, буквально часа.
Часа 3 назад, значит, этот студент, он мне сказал непосредственно перед лекцией.
Нет, он студент сказал, и Богачев сказал.
Ну, он скажет, ну хорошо, да, давайте.
Так, ну, видимо, у нас...
Наверное, мне надо связаться.
Так, сейчас.
А что, в расписании не написано, кто?
Есть такая проблема, вы как
Вот на это
тебе соединяться?
Вам просто на кнопочку нажать, я тоже...
В смысле? У меня компьютер, у меня там презентация.
Подсоединяться, это
Не знаю, проектор.
будет
Так, кто знает, как работает проектор? Так.
Ну, по идее, где-то должна быть кнопочка, которая опускается в эту штуку. Ну, такие, да. Они обе, наверное,
А вы говорите, дай бог, через 20 минут начнем.
Да, ну тут написано вообще 208, но написано, что именно 19.01 будет стоить 427. Ну вот это алгоритмы, то, что как раз и у нас, собственно, тоже написано.
Еще учебный офис решил переписать.
Расписание просто есть, как бы один курс по
А мы сейчас уйдем,
другой не 420.
А у вас будет все время здесь, да?
Нет, я думаю, что нет. Я думаю, что потом 208 будет так не будет.
А где? 408, может, туда перейдем?
У нас
Давайте только запись.
212, ну,
Людям пропустят.
Я вот абсолютно неопытный преподаватель, поэтому...
Ну, только что была лекция.
Рискну что-то изменить.
сейчас мы будем сейчас включать учебную часть.
Я сейчас звоню.
Сейчас, да, вряд ли что-то решим. У нас пара частей. Тогда, видимо, мы пойдем в 10:13.
Но следующее, начиная со следующего, вы, видимо, в другом месте.
Есть еще просто шанс, что людей перенесли из 208 сюда, потому что сейчас в 208 что-то тоже есть.
Нет, я так понял, потому что слишком много народу. За нами все равно 213.
Да, у нас 213.
Я звоню, видим, как сейчас все спросим.
Филипп Уваров.
Что такое?
Алло. Алло. Алло, Нина, здравствуйте. Говорит, Дмитрий, что это? Вот мы сейчас в 427-й аудитории. Есть два вопроса. Во-первых, также есть курс по группе Алгебры.
Я напишу Филиппу Уваров. Понятно. Ну, скорее
И
всего,
он спрашивает, как так? Кто сказал? Студент, который записывает, сказал, что сегодня все. Вот передо мной человек, который называется Филипп Уваров, потому что мне занятие. Как-то.
213.
Спасибо. Теперь второй вопрос. Мне нужно, чтобы все проекты были любому человеку знали, как это работает.
Я, кстати, не в курсе.
Так, а все, кто пришли, это курс по алгоритму, правильно? Так. Человек я вижу, а записалось в чате 45 человек. Как это понимать?
Там, наверное, 208 люди, может, не все знают.
А может быть, надо как-то сообщить?
Это уже сделано.
Вообще, в беседу написали уже. Ну, давайте схожу, тогда позову.
Я тоже в чате напишу, что... Вы эксперт, да? Вы эксперт по вот этой системе.
Ну, не эксперт, но...
Вот у меня есть компьютер, в нем